Log on, tune in, find out. Another good idea from Cambridge.
EPFL Lausanne will talk to us about periodic automorphisms of semisimple algebras.
Okay, thank you very much. Thanks for the invitation. Yes, as Gerhard says, so the title is Periodic Automorphisms of Semisimple Lie algebras. And so I've maybe slightly cheated with the title because there are a couple of bits that I missed off. I didn't want to scare anyone. What I really mean is that it's invariant theory of periodic automorphisms of semisimple invariant theory of or associated to periodic automorphisms of semisimple Lie algebras, so you could have reductive Lie algebras, but you don't gain a great deal with that. And so it's Lie invariant theory. I think it's probably a good idea for me to just maybe the idea of this subject is that if we take an automorphism of a semisimple Lie algebra, then we have these constructions which give you invariant theory, which is very similar to the invariant theory of the adjoint representation. So let me just remind you of the invariant theory of the adjoint representation. So for the moment, assume we're working over the complex numbers. Just take a reductive algebraic group. A reductive algebraic group, and then you consider the action of this group on its Lie algebra by the adjoint representation. And if we consider the invariance, the G invariance in the coordinate ring for the Lie algebra, then this is the coordinate ring of the categorical quotient of G by the reductive group G. Which I denote this way. And so the idea here is that we can relate the properties of this G action on the vector space G to familiar algebraic properties of elements of the Lie algebra G. So first of all, so the G orbit through a point X is closed if and only if X is semisimple. And of course, this is important when we're considering the categorical quotient, because the points of this quotient correspond one-to-one with the closed orbits of G on X. And so X is G unstable also if and only if X is nilpotent. And this gives us that the fiber of a 0, over the image of 0, is the nilpotent cone of G. Two things. So and so the Chevalier restriction theorem, which is probably the most famous result among all this, is that if we take a cotan subalgebra, so as I said, the closed orbits are the semisimple orbits, and since any semisimple element of G is conjugate to an element of the cotan subalgebra T, this gives us a way of relating closed orbits to W orbits inside the cotan subalgebra. And in fact, this is a bijection, and yeah. And the corresponding morphism is an isomorphism of varieties. So okay, and then perhaps traditionally one would probably say that in the following form, which is known as the Chevalier restriction theorem. If we restrict G invariant functions on the Lie algebra G to the cotan subalgebra T, then we get exactly an isomorphism onto the W invariant polynomials on the cotan subalgebra. Okay, just okay, let E be a regular nilpotent element, and then we embed that in an SL2 triple. And this is called E plus the centralizer of F. It's called the constant slice, and so we have lots of nice properties for this. It intersects each regular orbit in exactly one point. But the property that I'm interested in is the following: that if we just take we take the generators for the ring of G invariant polynomials on G, or there's something I've forgotten, and then we take the corresponding map from this constant slice onto the quotient, we get an isomorphism. So I forgot to mention that that the ring of W equivariant polynomials on T is a polynomial ring, which means that we have R equal to the dimension of T algebraically independent generators for this ring. So, okay, and so the idea, or the main theme of this talk is that in fact, given an automorphism of a reductive Lie algebra, or semisimple Lie algebra, we can quite easily construct an action of a reductive group G on a vector space, which has all of these nice properties. And in fact, this is not a new idea. This is a work of Winberg in 1976. My work has been, well, all of this on this page, everything except this construction of a constant slice is work of Winberg in characteristic 0. And in fact, this bit here, the equivalent of a constant slice, is a long-standing conjecture. So let me now introduce the main construction of the talk. So Winberg's work was over the complex numbers, and in fact there are some, he uses some properties of vector spaces over the complex numbers, which mean that even for other fields in characteristic 0, his results weren't immediately, you couldn't immediately deduce that they were true. And I take an automorphism of the group, really because this is a better construction in positive characteristic. But of course in characteristic 0, an automorphism of the group is more or less the same thing as an automorphism of the Lie algebra. So. Okay, so we take this automorphism of our group, and then we have the differential, which is also an automorphism of the Lie algebra, and a decomposition into weight spaces for this automorphism. So, of course, the most obvious example is when m equals 2. This is the symmetric space decomposition, which is very well known. Okay, so it's really very similar to symmetric spaces, except here we have lots of these subspaces G of I, and now G of 0 acts on each one. And so the first, what we're going to consider is the action on G of 1. And in fact, the action on any subspace, any of these spaces G of I, can be reduced to this case G of 1. So this is really, where generally we're just considering G of 0 acting on each of these spaces here. So as I said, the idea is that this has many similar properties, shares many of the properties that I wrote down for the adjoint representation before. So So first of all, closed orbits are semisimple orbits, and unstable orbits, those whose closure contains 0, are just the nilpotent ones. And then we want to have an analog of this Chevalier restriction theorem. So what would be a natural thing to choose? Well, as I said before, all semisimple orbits intersect non-trivially with this T, with the Cartan subalgebra. So we want to have something which is going to give you something similar, which is going to intersect non-trivially with each closed orbit. So we define a Cartan subspace to be a maximal commutative subspace consisting of semisimple elements. So it's all this bit which is maximal. So. And then so it's fairly obvious that any semisimple element of G of 1 is contained inside some Cartan subspace. So we just take the space generated by our semisimple element. This is commutative and consists of semisimple elements, so there must be some maximal one which contains it. So what's not so obvious is that any two Cartan subspaces of G of 1 are conjugate by this G of 0. And then, of course, this says that any given, if we fix a Cartan subspace, then any semisimple element of G of 1 is conjugate to some element of this Cartan subspace. Okay. So fix a Cartan subspace and then define this little Weil group to be the normalizer in G of 0 over the centralizer in G of 0. And so we have this equivalent of the Chevalier restriction theorem, a generalization really, because this case also includes the case of the adjoint representation. If we take two copies of G and just permute them, xy goes to yx, then we get something which is exactly the same as the adjoint representation. And so written in terms of the corresponding varieties, this is an isomorphism. And here I've written that it's just the set of WC orbits because WC is finite. So this really is the set of WC orbits on the Cartan subspace C. Okay, so the interesting thing here, some of you have probably seen this construction in relation to symmetric spaces where theta is an involution. And in that case, this WC is a Weil group of some kind. So for example, if we take the standard outer automorphism of GLN, then we get a Weil group of type In that case, we get a Weyl group of type A as well. But if we take the outer automorphism of GLN, which gives us the symplectic group, and we get, I think, a Weyl group of type B. But in fact, for general automorphisms, this is no longer necessarily a Weyl group, but in fact, it's a complex reflection group over the complex numbers. So because I'm working in positive characteristic, I prefer the term pseudo-reflection group. Okay, so that's the difference here with the theory of symmetric spaces, that really the results on orbits, things like nilpotent orbits inside this space G of 1, are much weaker than they are for symmetric spaces. But this relationship with pseudo-reflection groups is much more interesting. Okay. And therefore, in characteristic 0, we know by the Shepard-Todd theorem that the invariance of polynomial if and only if the group is a complex reflection group. Okay. Now, what I haven't mentioned for the moment is a bit that I've written about a slice, and so I'll come back to it a bit later. But quite soon after Winberg's work here, it was conjectured by Popov that we have something like a constant slice. So we have an affine linear subvariety of our G of 1, such that the embedding into G of 1 induces an isomorphism onto the categorical quotient. And I'll come back to that a bit later. Okay. Okay, so my aim in this work was to generalize Winberg's results to positive characteristic. And so what you have to assume, in order to have this this grading, if we're talking really about, I've wiped it off. If we're talking really about just about an automorphism of our Lie algebra of our group G, we need to assume that this automorphism has order co-prime to the characteristic. So assume theta has order m, not divisible by p. And then we just fix zeta instead of e to the 2 pi I over m. We just fix some primitive mth root of unity. Okay, we also have this grading, g of 0 up to g of n minus 1. And we can hope to generalize Winberg's results, all of these results, to positive characteristic, possibly under some assumptions on g and under certain assumptions on the characteristic. So that was the original aim of this work. Okay, and I just want to give you an idea of what the main hurdles in positive characteristic are. So the main problem is the ubiquitous problem in positive characteristic, which is separability. And so the problem with separability here is this morphism from C factored by the action of this little Weil group to the categorical quotient. Well, we can construct this morphism and we can show it's bijective. That's fairly easy. Difficult bit is to show that it's separable. Once we've shown that it's separable, these two varieties are normal, and then Zariski's main theorem tells us that it's an isomorphism. So that's one problem with separability, but it's not a very interesting problem to talk about. So I'll just pass directly to the second problem, which is broadly speaking, the failure of the Shepard-Todd theorem in positive characteristic. So, in fact, it's not only this. So, to give you a bit of an explanation, when Winberg proved that WC was generated by complex reflections, he used a certain argument about simply connectedness. So, if you take a vector space and take away the origin, if this vector space is of dimension 2 or greater over the complex numbers, then as a topological space, it's simply connected. Okay, fine. And of course, you can't do that over even a non-complex characteristic zero field. So I should stress that I'm always working over an algebraically closed field. Now, Panyashev solved that problem in characteristic zero using a Tal cohomology. So similar argument. We have this C factored out by the action of WC, and if we take away the origin, it's Winberg said that it's simply connected, and we can use this to show that it must be a polynomial ring, or the invariance must be a polynomial ring. Panyashev's result applies if we know that this group WC has order not divisible by the characteristic. So okay, and so the main approach was to describe WC directly for the classical types. This had already been done by Winberg, but I'll explain a bit about why my approach was different to Winberg's a bit later. For the exceptional types, as I said, the result of Panyashev is okay if we know that the order of WC is not divisible by the characteristic. And so the main approach here is to say, well, suppose we take our Cartan subspace C and we put it inside a Cartan subalgebra. And suppose this Cartan subalgebra is also stable under this automorphism of the Lie algebra. Well, then we have something, if it's an inner automorphism, then it's acting by an element of the Weil group. So it's acting by an element of the normalizer of the Cartan subspace. And then this WC is going to be related in some way to the centralizer of that element inside the Weil group. So for exceptional types, it's actually not a very difficult task to look at Carter's classification of conjugacy classes, and assuming that assuming P is good for G, for the root system of G, which means that for exceptional types means that P is greater than 3, and if G is of type E8, then P is greater than 5. And then, in fact, it's fairly easy to check that, that this the centralizer of the element doesn't have order divisible by P. And so I think you can say that the difference between my approach, also for the first part, in describing this, little Weyl group for the classical types, the difference between my approach and Winberg's approach is more or less that I consider WC in relation to centralizers of elements inside the Weyl group. Winberg describes the automorphisms differently. He says, well, suppose we have an inner automorphism. We can describe this as conjugation by an element of the maximal torus. And in fact, I think I'm going to go straight to an example. So suppose theta is just conjugation by this element here, where we have 2 copies of each of the powers of zeta. So it's fairly easy to write down what g of 0 is and to write down what g of 1 is. G of 0 is that. And G of 1 is that. And Winberg's approach was to say, well, let's try and construct a Cartan subspace which lies inside this G of 1. So in this case, you would take, well, no, I don't want to write it down or tell you because it'll take too long. But it's possible to construct a Cartan subspace inside here, and then, well, let's try and work out what the normalizer is inside G of 0. And so it's not too surprising that with that approach, Winberg didn't give that many details of the calculation. But, okay. Okay, my approach is to say, well, let's look at X and say this is conjugate to an element of the normalizer of a maximal torus. So Okay, it's conjugate to this element, and we can see how this acts on a maximal torus. It's just a product of two M cycles. So okay, and now, so first of all, it's not too difficult to work out what the centralizer of this is inside a symmetric group on 2M letters. But we can, in fact, more specifically, we can actually give a basis of our Cartan subspace C. So and C has a basis consisting of those two elements. And in fact, if we let we consider those three elements, then we can very easily describe the action of these elements on the two elements of the basis. So we have zeta 0, 0, 1, 1, 0, 0, zeta, and 0, 1, 1, 0. So this is not actually quite direct. We need to do some more work. This tells you how the centralizer of Y in the Weil group acts on the Cartan subspace. And so in general, the little Weil group WC is a subgroup of the centralizer in the Weil group factored out by the elements inside that centralizer which act trivially. So it can actually be a proper subgroup. Okay, so that gives you some idea of the difference in approach. This is this is just a special case. So in type A for inner automorphisms, it's actually quite easy. It gets a bit more difficult when you start looking at outer automorphisms or automorphisms of type D. But okay. So just to be absolutely precise about the main conclusions, this paper was accepted yesterday, so I think you can say that this is okay. So the main isomorphism of the Chevalier restriction theorem, we need to assume that the characteristic isn't equal to 2. So in fact, this can be seen if we look at SL2 in characteristic 2, then this isomorphism doesn't hold. It's a purely inseparable extension, in fact, for SL2. The reason is because for SL2 in characteristic 2, the Weil group acts trivially. So, okay, and if we assume that G satisfies the so-called standard hypotheses, so we assume that P is good and that the derived subgroup is simply connected, and that there's this a G equivariant bilinear non-degenerate symmetric form on the Lie algebra, then it's not particularly strong hypotheses, then yes, we know that the little Weil group is generated by pseudo-reflections and that there's this isomorphism. So, and for the cases that I talked about, so if P doesn't divide the order of WC, then this is an immediate application of the Shepard-Todd theorem. So for the other cases, it's not too difficult to show directly that WC, for example, in this case, if we had GM1R, well, the invariants are generated by the elementary symmetric functions in the mth powers of the coordinates. So, okay, now I want to talk about so this is generalizing Winberg's result to positive characteristic. That's all very well. But this change of perspective, this different approach actually gives us something else, which I mentioned before, which is the existence of a slice which is somehow akin to constant slice to the regular orbits in the adjoint representation. So okay, so we've already seen that the invariance, the ring of invariance is a polynomial ring, and that means that the categorical quotient is isomorphic to a vector space. And so what looks like a much stronger property is to have some affine linear subvariety of G of 1 which maps isomorphically onto the categorical quotient. What that means really is if we take a set of basic invariants for the action of G of 0 and G of 1, and we restrict these to this affine linear subvariety, then they look something a little bit like coordinate functions. Not exactly, but something a bit like that. And so this is obviously a nice property to have. So this conjecture of Popov is that there always exists something like a constant slice, so something which, a KW section. And so this conjecture has been proven, obviously, in characteristic 0 because it wasn't known that this also holds in positive characteristic until now, in two cases. So firstly, when G of 0 is semi-simple, and so this is, I think, quite a restrictive case. And then the second case is when is what's called the n-regular case, when this space G of 1 contains a regular nilpotent element of G. So that's quite a rare case, but so I should maybe say that if we look at an involution, then this condition that G of 1 contains a regular nilpotent element of G is equivalent to the condition that G of 1 contains a regular semisimple element of G. So n regular and s regular are equivalent in that case. But in general, that's not at all true. And we can see this quite easily if we just take the grading of GLN, where the one space is just the first upper diagonal. So this contains a regular nilpotent element, but contains no semisimple elements. And this is probably the main difficulty of proving Popov's conjecture in full generality, that we don't have this easy way of reducing to the S-regular and N-regular case. So And so we can prove 2 also in positive characteristic. And the idea, as I said, if we take this constant slice, which is E plus the centralizer in G of F, that's the slice to the regular orbits, which maps isomorphically onto the adjoint quotient, the quotient of G by its group G. And so the idea is to kind of restrict one of these slices to our space G of 1. So this is the idea. We pick an SL2 triple with the H in the 0 part and F in the -1 part. And then we look at E plus the centralizer in G of 1 of F. And that's exactly. So in positive characteristic, we actually need to be a bit careful. It's not this Z centralizer of F, but it's some subspace of the negative part for the H grading, which is transverse to the G orbit through E, something like that. Okay, and so the main advantage of, well, the main point of this final section is to say that everything I've done before, a case-by-case analysis of what WC looks like, and relating it to centralizers inside the Weil group, gives us a way of reducing the proof of the existence of a KW section to this case here, the n-regular case. So. Okay, so this is a very vague statement that we're throwing away unnecessary information. So for example, if we take a GL n where n is greater than 2m, and we take the example that I had before, where W is a product of 2m cycles, well, we still get the same group, G of m1, 2. And the idea really is that we can throw away the parts of n which are greater than 2m. So we can just reduce directly from GLn to GL2m. And in fact, once we do that, we're in exactly this case here, which is n regular. So for inner automorphisms of GLn, this is quite easy. For other automorphisms in classical types, it gets a little bit more difficult. But the same principle applies. That in fact, this analysis of the Weil group shows us that we can reduce to a minimal case, and the minimal case is the n regular case. So the main conclusion is that KW sections exist for G classical. So this wasn't known in characteristic 0, but the proof holds also in odd positive characteristic as well. I just want to say a little bit more about, because we can say a bit more than this, in fact. So when we look at the classical case, these the little Weil group WC is not, I would say it's not particularly interesting. It's one of the groups GM1R or GM2R or something like that. So, okay, that's interesting enough. But when we look at exceptional types, we start to get some of the exceptional groups on the list of Shepard and Todd. So. And so it's actually quite I think this is quite a common phenomenon. So I spoke to Gunther Meller, I don't think he's here, and he said that he studied in the 90s looking at the actions of centralizers inside the Weil group on some subspace or some subgroup of an exceptional type. algebraic group. And in fact, he came up with quite a similar phenomenon. When you look at centralizers, you get some complex reflection group. But it's quite a nice little exercise. Now that we know that this group has to be a complex reflection group, you can actually read off the orders of centralizers inside the file group from Carter's tables, and it gives you some quite interesting cases. So I've done this for types F4, G2, and D4, 3, I mean the triality automorphisms in D4, which I don't consider to be automorphisms of a classical group because they're not automorphisms of SL8. So and in fact, this classification, we can also show that there always exists a KW section in these cases. So, and this leaves the problem open only in type E. Okay, thanks a lot.
Can you say again which groups occur in the classical
Yes,
test? You said G.
And these ones, so you have, I think number 5 appears for an automorphism of order 3.
The number 5 appears in which?
For F4.
Uh-huh.
For an automorphism of order 3, you get number 5, and then this is also an automorphism
the
of
group
D4.
called G5 occurs.
Yeah.
Is that what you mean? Okay.
Yeah, exactly.
Uh-huh.
But then this automorphism also gives you an automorphism of D4, and in that group you get type 4. So, number 5. I have the tables upstairs. Okay. So number 5 appears.
Uh-huh.
Yeah.
But so in the classical types, you said you only get GM1R and
GM2R, or possibly you have to divide or multiply n by 2. So that's, yeah.
Okay, so that's okay. So even if I guess for GM2R to be defined, M has to be even.
Yeah.
But even if M has many other factors, you just don't see them.
No.
Okay.
What's involved if you want to complete this with the exception?
Well, either lots of case checking or a conceptual proof, which would be better. No, it should be possible to. In fact, I don't want to say too much because maybe I've made a mistake, but I think it's okay. You can use some kind of induction to reduce to a small number of cases, and it should be okay.
Do you think it's possible?
Yeah.
And you expect again there's always a
Yeah.
So in particular, these groups don't have to be spatial.
I don't think so. I'm not sure. In fact, I can give you the list. But
So I guess G5. So G5 is not.
It's not.
spatial.
Okay, then they don't.
That-
Yeah. Yeah, G5. So G5,
and
G8, G4.
GM2R is not spatial
Right.
unless
Okay.
M is 2.
Okay.
No further questions? You again.